Imagine a world where your every step, every gesture, powers the devices that define your digital life. This isn't science fiction, it's the cutting edge of energy harvesting from human motion. We're talking about capturing the kinetic energy generated by our bodies and converting it into usable electricity. This revolutionary approach promises a sustainable, renewable power source, especially for the ever-expanding universe of portable and wearable electronics. Our modern lives are increasingly intertwined with electronic devices. From fitness trackers to smart implants, the demand for ubiquitous, always-on technology is soaring. However, this convenience often comes with the constant hassle of recharging or replacing batteries. This reliance on external power sources presents significant limitations for device longevity and user experience. The concept of energy harvesting from human motion offers a compelling solution. It aims to create truly self-sufficient devices, liberating them from the grid. This paradigm shift is crucial for the next generation of wearable tech, IoT sensors, and even implantable medical devices. It promises unprecedented freedom and reliability for our digital companions. The field of human motion energy harvesting is a vibrant arena of material science and engineering innovation. Researchers are exploring diverse physical principles to convert mechanical energy into electrical power. Each method offers unique advantages and is suited for specific applications, pushing the boundaries of what's possible. Tangs are at the forefront of flexible and cost-effective energy harvesting. They leverage the triboelectric effect, a phenomenon where certain materials become electrically charged upon contact and subsequent separation. This charge transfer occurs when two different materials rub or touch, creating an electrostatic potential difference. The beauty of tangs lies in their simplicity and versatility. They can be fabricated from common, inexpensive materials like polymers, textiles, and even adhesive tape. When these materials are subjected to mechanical deformation, such as bending or pressing, they generate an electrical current. This makes them ideal for integration into clothing or footwear. Researchers are developing various T&E configurations, including contact separation mode, sliding mode, and single electrode mode. These designs allow for efficient energy capture from diverse human movements, from walking to finger tapping. The output can then power small sensors or charge microbatteries. PENGs harness the piezoelectric effect, a remarkable property of certain materials that generate an electric charge when subjected to mechanical stress. Conversely, they deform when an electric field is applied. This direct conversion mechanism makes them highly efficient for specific applications. Common piezoelectric materials include lead zirconate titanate, PZT, polyvinylidene fluoride, PVDF, and various ceramics like barium titanate. These materials can be integrated into flexible films or fibers, making them suitable for wearable applications. When a peng embedded in a shoe sole is compressed during walking, it generates electricity. Pengs are particularly effective at converting high-frequency vibrations into electrical energy. However, ongoing research focuses on optimizing their performance at the lower frequencies characteristic of human motion. Their high power density and rapid response make them attractive for powering dynamic sensors and actuators. This method relies on the well-established principle of electromagnetic induction, where a changing magnetic field induces an electric current in a conductor. In the context of human motion, this typically involves a magnet moving relative to a coil of wire, or vice versa. The kinetic energy from body movements drives this relative motion. A key challenge for electromagnetic harvesters is the low frequency and irregular nature of human motion. To overcome this, innovative designs incorporate frequency-up conversion mechanisms. These mechanisms convert slow, large amplitude human movements into faster, smaller amplitude oscillations, optimizing energy generation. Examples include pendulum-based generators or linear generators integrated into backpacks or clothing. As the body moves, the internal components oscillate, generating electricity. While often larger than nanogenerators, electromagnetic harvesters can provide higher power outputs for certain applications. Pushing the boundaries of miniaturization, ultra-thin energy harvesters represent a significant leap forward. These systems are often based on advanced material science, utilizing layers just a few atoms thick. They are designed to generate electricity, even from subtle low-frequency movements, characteristic of human activity. These harvesters can be incredibly flexible and conformable, making them ideal for integration into smart textiles or even directly onto the skin. They might combine principles of triboelectricity or piezoelectricity within their ultra-thin structures. The focus is on maximizing surface area and material interaction within a minimal footprint. Their ability to operate efficiently at low frequencies is a critical advantage. This means they can capture energy from everyday actions like breathing, subtle muscle contractions, or the gentle bending of a finger. This opens up possibilities for truly pervasive and invisible energy harvesting solutions. The implications of human motion energy harvesting are vast, promising to revolutionize how we power our personal electronics, medical devices, and smart environments. These technologies are not just about convenience. They are about enabling new functionalities and improving quality of life. The proliferation of wearable sensors for health and fitness monitoring is a prime application. Imagine a continuous glucose monitor powered entirely by your body's movement, eliminating the need for battery changes. Energy harvesting can power sensors that track heart rate, body temperature, blood oxygen levels, and even metabolic byproducts. These self-powered sensors could provide uninterrupted data streams, offering more accurate and comprehensive insights into an individual's health. This continuous monitoring is invaluable for preventative healthcare, athletic performance optimization, and managing chronic conditions. The reliability of self-powered devices enhances their utility significantly. Smartwatches and fitness trackers are ubiquitous, yet their battery life remains a common complaint. Energy harvesting systems can be seamlessly embedded into these devices. Kinetic energy from arm swings, wrist rotations, and even typing can be converted into electricity, continuously topping up the device's battery. This would dramatically extend battery life, potentially leading to devices that never need to be plugged in. Users could enjoy uninterrupted access to notifications, health data, and smart functionalities. This enhances the user experience and reduces the environmental impact associated with frequent charging. The concept of smart clothing moves beyond mere aesthetics, integrating technology directly into our apparel. Ultra-thin energy harvesting systems can be woven into fabrics, creating garments that generate power as you walk, run, or simply move throughout your day. This transforms your attire into a personal power generator. Imagine a jacket that charges your smartphone as you commute, or athletic wear that powers integrated performance sensors. This seamless integration means personal electronic devices could be powered passively without conscious effort. Smart clothing could become a hub for personal energy generation and distribution. Perhaps one of the most profound applications lies in implantable medical devices. Pacemakers, neurostimulators, and various biosensors currently rely on batteries that require surgical replacement every few years. This is invasive, costly, and carries inherent risks for the patient. Energy harvesting from internal body movements, such as heartbeats, blood flow, or diaphragm motion, could provide a continuous power source. This would eliminate the need for repeated surgeries, significantly improving patient comfort and safety. It represents a monumental leap forward in long-term medical care. Beyond personal devices, energy harvesting is critical for the widespread deployment of Internet of Things, IoT nodes. Imagine smart city sensors, environmental monitors, or structural health sensors that never need battery replacement. These nodes could be powered by ambient vibrations, wind, or even pedestrian traffic. This enables truly pervasive sensing networks that are sustainable and maintenance-free. Such self-powered IoT nodes are essential for smart infrastructure, precision agriculture, and large-scale environmental monitoring. They reduce operational costs and expand the reach of connected technologies. While the promise of human motion energy harvesting is immense, several challenges must be addressed to realize its full potential. Researchers worldwide are actively working on these hurdles, pushing the boundaries of material science, device design, and integration. A primary challenge is improving the efficiency of energy conversion and increasing the power output of these devices. Human motion is often low frequency and irregular, making it difficult to harvest substantial amounts of energy. Current devices typically generate microwatts to milliwatts, sufficient for low-power sensors but not yet for power-hungry devices. Future research focuses on optimizing material properties, device architectures, and resonance mechanisms to maximize energy capture. This includes developing new composite materials and designing multimodal harvesters that combine different energy conversion principles for enhanced output. The goal is to achieve higher power densities from subtle movements. Many energy harvesting devices produce relatively low voltage outputs, often in the millivolt range. For practical use, this voltage needs to be stepped up to levels compatible with standard electronic components, e.g., 1V to 5V. This requires efficient power management circuits that can boost and regulate the harvested energy. Developing ultra-low power voltage converters and energy storage solutions, like supercapacitors or thin-film batteries, is crucial. These circuits must be highly efficient to avoid wasting the precious harvested energy. Miniaturization of these power management units is also a key area of development. For wearable and implantable applications, energy harvesting devices must be highly flexible, lightweight, and conformable to the human body. They need to withstand repeated bending, stretching, and compression without degradation in performance. Traditional rigid electronic components are unsuitable for these dynamic environments. Research is heavily invested in developing flexible substrates, stretchable conductors, and soft active materials. This includes integrating harvesters directly into textiles using advanced weaving or printing techniques. The aim is to create devices that are imperceptible to the user, seamlessly blending into clothing or skin. The quest for superior materials is continuous. Researchers are exploring novel polymers, ceramics, and composite materials with enhanced triboelectric, piezoelectric, or electromagnetic properties. The focus is on materials that are not only highly efficient but also durable, biocompatible, and environmentally friendly. The use of nanomaterials such as nanowires, nanotubes, and graphene is particularly promising. These materials offer high surface, area to volume ratios and unique mechanical properties, leading to improved energy conversion. Developing scalable and cost-effective manufacturing processes for these advanced materials is also critical. The true power of energy harvesting devices emerges when integrated with artificial intelligence, AI, and the Internet of Things, IoT. Self-powered sensors can become intelligent nodes within vast networks, collecting data autonomously and transmitting it wirelessly. This enables truly smart environments and personalized health monitoring. Imagine self-powered smart patches that monitor vital signs, analyze data using on-device AI, and alert medical professionals only when necessary. Or smart clothing that adapts its properties based on real-time environmental data. Powered by your own movement, this synergy creates a future where devices are not just connected, but also self-aware and self-sufficient. Hey, if you're enjoying this video, and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.